Hi, this is Nelson Yanofsky. The class is Discrete Structures. We're up to section 13.2, which is Elementary Predicate Calculus, all about quantifiers and stuff like that. These are the homework problems we're going to do. Just make sure I'm focused right. Okay, lots of word problems. But pretty much easy. Okay, consider the universe U of all college students. Okay, so this is number 2. So the universe of discourse is all college students, and we say P of X means X likes broccoli. Okay, I don't know how to spell broccoli. B-R-O-C-C-O-L-I. Okay, it likes broccoli. Okay, now what you want to do is say, express the propositions, not all college students like broccoli. Okay, so another way of saying that is, it's false to say that everybody likes broccoli. Okay, so that's the answer to that. Not all college students like broccoli. So this is all college students like broccoli. This is not all college students like broccoli. Can't get easier than that. Next, do the same for every college student does not like broccoli. Okay, so let's do this. B, every college student does not like broccoli. Makes sense. Okay, great. Now, C, does either of the propositions in part A or B imply each other? Let's go through it. Question. Does this imply this, or does this imply this? Let's see what it says. Okay, by the way, we know the answer already because we know about Demorgan's law, but let's just do this. Not everybody likes broccoli. Okay? Does that mean everybody does not like broccoli? No, it doesn't mean everybody. Let's say there's 3 students who don't like broccoli. Okay, then this is true, but this, everybody does not like broccoli. No, 900 students do like broccoli, so this does not imply that, so that doesn't imply that. How about going this way? If everybody does not like broccoli, does that mean that it's false that everybody likes broccoli? That could be, that works. Ready? If everybody doesn't like broccoli, does that mean it's false that everybody likes broccoli? I think it works. Okay, but so this part does work. I just want to say, this part, this we saw is equivalent to, by Demorgan's law, there exists an X such that not P of X. Right? This comes across and becomes like that. Now watch this. This makes sense. If I say for all X, not P of X, that's this, that implies there exists an X, not P of X. Let's see how this works. If I tell you everybody has something, that means one person has it for sure. If I tell you everybody is not handsome, that means there is somebody who's not handsome. It doesn't go the other way, but this always works. Okay, so this way it works. Okay, great. Okay, D, write out the meaning of the rule 37b for this universe and P of X. 37b. Okay, 37b is, hold on, so we're still doing number 2. 37b is, it's false that E of X, P of X implies, this is one of the Demorgan's law. If and only if. Okay, this is one of the Demorgan's law, but now they want to talk about college students and broccoli. It's false that there exists somebody who likes broccoli is the same thing as, I'll say it again, it's false that there's somebody who likes broccoli means everybody hates broccoli. Let's do that again. If it's false that there's somebody who likes broccoli means everybody does not like broccoli. Okay, if you can find one person that likes broccoli, that means everybody doesn't like broccoli. Okay, you go the other way around. If everybody doesn't like broccoli, that means there's not one person exists who likes broccoli. Okay, I want you to do it for the other one also. Hold on. Do the same for 37D. If you have there exists P of X, it's false that for all X, false P of X. Okay, what does it say? If there's somebody who likes broccoli, if there's somebody who likes broccoli, it means it's false that everybody doesn't like broccoli. If there's some college student who likes broccoli, that means it's false that everybody doesn't like broccoli. Okay, that's it. So that takes care of number 2. Oh, and you can go the other way too. Okay, number 4. Before we did 4A in class, but let's do 4B. Okay, so it says as follows: P of M comma N stands for M is not equal to N. Okay, we did the first one. Let's do the second one. Okay, the domain of discourse is the natural numbers 0, 1, 2, 3, 4, etc., etc. Let's see what this is. It's false that for all M there exists an N such that, well, I'm not going to write P of M again, I'm just going to write M is not equal to N. Question: does that imply that it's false that there exists an N such that for all M, M is not equal to N? Okay, now got to figure out what this means. So let's do this. Let's close this off and, okay, again, the outermost operation is here. So we want to know, question, does this imply this? Yes or no? Okay, so first we have to figure out what this is, and then we have to figure out what this is. So let's see what this says. This says, so let's close this off for a second. For every M, there is an N such that M is not equal to N. Is that true or false? For every M, given any number whatsoever, 53, does there exist a number N such that M is not equal to it? And the answer is yes. Why? Because 53, 28 is not equal to it. 42 is not equal to it. 127,000 is not equal to it. Okay, so this statement is true, which means this statement is false. Okay, with the not is false. If this is true, then with the not it's false. Okay, just for the hell of it, let's bring the quantifier in. We showed how to do that and see what it says. This is the same thing. It's logically equivalent to, okay, bring the quantifier in. Okay, so what does this say? This says there exists an M such that for all N, again, when the not goes past the quantifier, it switches the quantifier. Okay, and then it's going to be not M is not equal to N. So this is going to become M equals N. Okay, let's see. Is there some number that for every number M is equal to N? Is there some number M such that every number is equal to it? No, that's stupid. There's no single number that's equal to every other number. That's crazy. So this is false. Okay, by the way, I don't even have to evaluate this because false arrow anything, 0 arrow anything is true. So I can tell you now the answer to this is true. Okay, but that's a little lazy. So let's capture. That's called lazy evaluation, right? false and arrow anything is true, so I might as well not do this. But let's just understand what this is true. Is this true or false? Let's close off that not and see is this. Is this true? There exists an n such that for all m, m is not equal to n. Is there some number that is not equal to any other number? Is there some number that is not equal to any other number? And the answer is no. The number 23, it's not true that nothing's equal to 23. 23 is equal to 23. So this is false, which makes this true. So this is true. So false arrow, true is true. That's the end. Again, let's just do this the same way we move the quantifier in. Let's move the quantifier in and see if we can make this statement a little bit clearer. It says for all n, there exists an m such that that changes, when we cross this, we change it from an existential quantifier to a universal quantifier. When we cross this, we change it from a universal quantifier to an existential quantifier. And when we put not m is not equal to n, that means m equals n. Okay, now is this statement true or false? For every number n, is there a number m that's equal to n? And the answer is yes. That number in particular. So give me a number. 43. How about 43? 43 is equal to 43. So this is definitely true. Okay, great. Okay, we got to search for a good marker. These markers are not good. Okay, so that's 4A. 4A we did in class. 4B. Okay, 4C has an error in it. Okay, let's do 4C. 4C has an error. So 4C is for all, bad. Hold on. For all n, P-M-N. Okay, this is what it says in my version of the book. P, M, comma, N. Now it's not this, okay? And the reason why it's not this is because M, I don't know what M is. Okay, so this must be a mistake and this must be N. Okay, now question, is this true? Is it true that for all N, N is not equal to N? That's the silliest thing in the world. How can a number not equal to itself? Every number equals itself. So this is false. Okay, great. Let's do D. D looks like a pain in the neck. Okay, let's do it. D says, for all m, it is false that for all n, m is not equal to n, or there exists an n such that m is not equal to n. Okay, question, is this true or false? We actually have to go through it very carefully. Okay, we're going to use other colors. Okay, so let's see. For all m, we're going to put parentheses around here, and parentheses around here. Okay. Okay. For all m, does there exist an n such that m is not equal to n? This is true. For all m, every m, there's another number that's not equal to it. So this is true. So already, the whole thing is true, because if this is true, then or this is true. But this is let's see, this is a little bit more complicated. For all m, it is false that every n is not equal to it. Let's close that off. Every n is not equal to it. Give me any number, then any number is not equal to it. That's not true. So this is true also. Okay. So if you close off if you forget about the not, this is false. Therefore, if you have the not, it's true. Okay. So this is true and this is true. Both of them are true. Okay. So that takes care of that. Okay, so that was problem number 4. Okay, they just want you to get used to understanding the meanings of these formulas. Next, we did 2, we did 4, now let's do 6. 6 I did in class. Okay, but they want something like this. Okay, 6b. 6b, they want something like this. There exists an x such that for all y, that implies that for all x, there exists a y p of x comma y, p of x comma y. So listen to what they say. Show that this is false. Okay, they want you to find a predicate p of x y that we did it. That shows that it's false. We did this already. We said love. So let's say p of x y is equal to love of x y. Okay, x loves y. Look what this says. This says if there's someone who loves everybody, does that mean that everybody loves someone? Let's do this. If there's someone who loves everybody, so let's say Mother Teresa loves everybody, does that mean that everybody loves someone? Okay, and that's not true. I don't love someone, whatever. Not everybody loves somebody. There could be one person who loves. But this way is, so this is false. This way is true. Let's see. No. If everybody loves somebody, that means that there's one of those people loves everybody. No, that's not true either. Okay, this is different than what we did in class. But anyways, the love thing shows that this is false. Okay, good. 6 we did. Next, 7. Next, 7. The universe, let's cross it out. Okay. The universe of discourse is the natural numbers. Write the negation without using the quantifier for all. Okay, so look what it says. For all n, p of n, oops, p of n implies p of n plus 1. This is called the domino thing, actually. So what does this say? If the nth one is true, then the nth plus 1 is also true. Whatever p stands for. Okay, but listen to what they want. Write the negation without using the quantifier. So they want you to take this statement, write the negation of it, but this has a quantifier, the universal quantifier. Anyways, so what they want is like this. Bring that across. So that becomes, there exists an n such that it's false that p of n and p of n plus 1 implies p of n plus 1. Now technically we're finished the problem. Okay? That's it. We don't have the universal quantifier. What they really want is, they didn't say it properly, they want you to get rid of this also. So let's get rid of it. Okay? How do we say that this statement is false? How can this statement be false? Again, think of it as you have an infinite row of dominoes, and this says if you knock down the nth domino, then you're going to knock down the nth plus 1th domino. If you knock down the n plus 1 domino, you're going to knock down the n plus 2 domino. You're going to keep on doing it. How do you say the negation of that? Well, the negation of that is, well, again, how do you say this is false? This is false if this is true. If this is true and this is false. So that's the same thing as saying there exists an n such that p of n is true and not p of n plus 1. Okay, which means what? There is some domino. If it's false that all the dominoes knock down their neighbor, that means there is some domino, there exists a domino, such that when it goes down, it doesn't matter because this next one will not go down. So that's an interesting thing. Okay, you can't really get rid of this not because we don't know what P stands for. So we can't go inside. Great, let's do number 9. Number 9. Okay. Okay, so let's see. This is number 9. We have a formula, P. The formula stands for as follows. For all x, for all y, if x is less than y, that implies there exists a, there exists a z such that x is less than z which is less than y. Okay, let's see what it says. It says for all x, for all y, if x is less than y, that implies that there is some number z such that z is in between them. X is less than z and z is less than y. So if you, as long as you have two numbers, one less than the other, there's another number in between. There exists a number in between. Great. That's what the statement says. That's what the statement means. Now it wants us to write the negation of it. So not P is equal to, let's write it out, not for all x, not for all y, x less than y, arrow, there exists a z such that x less than z less than y. Okay, great. Okay, now let's bring the negation in across the quantifiers. So this becomes not P, this becomes, let's say it's equal to, there exists an x, there exists a y, such that this is false. Now, again, how do we say this is false? How do you say an arrow is false? If the first thing is true and the second thing is not true. Okay, so let's do this. You ready? If the first thing is true, x less than y, and the second thing is not true, it's false that there exists a z such that x is less than z, which is less than y. Okay? Okay? So we just brought this across. Let's just say it again. What does it say? Look what this says. It says, for any two numbers, if one is less than the other, there's something in between. Now look what it's saying. The false, saying that this is false means there are two numbers such that x is less than y, but still there's nothing in between them. What does it mean there's nothing? There does not exist a z such that x is less than z, which is less than y. So let's write this, let's bring this quantifier across. That means for all z, okay, either x is not less than z, or z is not less than y. Yeah. Okay. Anyways, so that's the way to do it. That's the negation. Okay. They don't like the word negation, so you can swap that. You say z is less than x, or z is more than y. Let's write that. Z is less than x, or equal to, or z is more than or equal to y. Okay? In other words, here's x, here's y, then either z is here or z is here, but z is not in the middle. That's what it means. So that's the negation. Okay, great. Now, part 2. Determine the truth of P when the universe of discourse is the real numbers or the fractions. Okay, so let's do this. Okay? So here's P. Question, is it true in the real numbers? Okay, let's go through that again. What does it mean? It says, given any two real numbers, if x is less than y, there's some number in between them. Is that true? Okay, first day of 9th grade. Okay, what do? This is your real number line. If you have an x over here and you have a y over there, there's definitely going to be something in between. Okay, same thing with fractions. Given any two fractions, there's always a fraction in between them. So they're both true for real numbers and for fractions. Next, 9C. What about for Z, those whole numbers, or the natural numbers? Okay, is it true that given any two numbers, if one is less than the other, there's something in between? Whole numbers. Is it true or false? False? Why?
Because it could be like, could be that there's like 1 and 2.
Right, 1 and 2. Or how about this? 53 and 54. There's not. 53 is less than 54, but there's nothing in between. Okay? And negative, well, even negative numbers too. So there could be two whole numbers, one next to each other. There's no whole number in between. Okay? Great. So for these two things, it's false. But for real numbers, it's true. And for fractions, it's true. Okay, great. Last problem, number 10. Number 10. Give a counterexample to each of the following assertions. Okay, let's write it. Okay, so they give you nice English, and they want you to show it's true. Every even integer is the product of two even integers. Every even integers is the product of two even integers. It's false. Give me a counterexample. Give me an example that shows that it's false.
What's integers?
Integers are whole numbers. Okay, and the answer is every even 2 times 3 equals 6. This is an even integer. It's not the product of two even integers. It's the product of an even and an odd. You do need one to be even. So this 6 is a counterexample. It shows that it's false. Okay, number B. The number of elements in this. You have two sets. Okay, you have two sets. The number of elements in the union of the two sets is equal to the number of elements in S plus the number of elements in T. Is that true or false? Okay, and the answer is it's false. Why? Because if this is the set S and this is the set T, then the union is those things in here or in here. Great. What's this? That's this guy's plus this guy's. You're going to count these twice. You're going to count the intersection twice. So let's just give an example. If S is equal to A, B, and T is equal to B comma C, then the number of elements in S union T is 3, and that's going to be 2 plus 2. 3 is not equal to 2 plus 2. So that's a counterexample that shows that this is false. Next, every positive integer of the form 6k minus 1 is prime. Every positive integer 6k minus 1 is prime. I don't know. I don't even know if it's true. Let's see. K is equal to 0. No. 6 times 0 minus 1 is 0. So that is negative 1. So that doesn't work. k is equal to 1, so 6 minus 1 is 5. 5 is prime. So let's do 5 is prime. So k is equal to 1. This is k is equal to 1. Let's do k is equal to 2. 6 times 2 is 12. 12 minus 1 is 11. 11 is prime. Maybe it's true. 6 times 3 is 18. Minus 1 is 17. 17 is prime. 6 times 4, this is troubling. 6 times 4 is 24. Minus 1 is 23. 23 is prime, yes or no? Yes. Okay, so k is equal to 5. 6 times 5 is 30. Minus 1 is 29. Is 29 prime?
Yes.
I think it is. Okay. K is equal to 6. 6 times 6 is 36. Minus 1 is 35. 35 is prime or no? 35 is 7 times 5. Okay. So that's that's the counterexample. K is equal to 6 is the counterexample because it's not prime.
This is a very big counterexample.
It's a very big counterexample. Yeah, I would have thought we would have found it earlier. K is equal to 6 is a counterexample. Okay, every graph has an even number of edges. Every graph has an even number of edges. 1, 2, 3. That has an even number of edges. That has an odd number of edges. Finished. I'll give you a smaller counterexample. That has an odd number of edges. That was a silly problem. Okay, all mathematics courses are fun. No counterexamples there. Anyways, but we teach you computer science, so that's take care of that. Anyways, as always, I hope you enjoyed.